Hello. The topic of this video is going to be what is geometry, illustrated by axioms and what you can and can't do with them. From this modern geometry book, I'll show off the title and author information a little later. Here in the back of the book we have a list of axioms. From these axioms, which it's easy to go over in a relatively brief span of time, all of Euclidean geometry is based. You see, we begin with three incidence axioms, so-called. Then we go to some axioms concerning betweenness. Now let me turn the page here. We must pick up, for the sake of completeness, a couple more betweenness axioms listed on this page, B3, B4. Also, we need to add yet more what are called 6 congruence axioms, as we see here. Then on this page we must have one of the continuity axioms. Deduction's axiom here is preferred in this section. And in terms of the parallelism axioms in this section, you really only need Hilbert's parallel axiom for Euclidean geometry. This is a modern presentation of the axioms upon which Euclidean geometry was based, is based. It is more rigorous and more definite than what you find in geometry traditionally, going back to the ancient Greek development of the subject with Euclid. They did in the 1800s, 1900s, that some of Euclid's reasoning in his foundational book of geometry, written back in the era when the Greeks first began to investigate geometry, some of his proofs, though admirable as far as they went, were not sufficiently rigorous enough logically. And people such as Hilbert, David Hilbert, great German mathematician, did what they had to do to fix the problem of the incompleteness of Euclid's axioms. And this is the book here that I took this from. I think I have an edition from the 1990s, Euclidean and Non-Euclidean Geometry's Development and History, 3rd edition, Marvin J. Greenberg. Excellent book in its way. Now, that's the axiomatic basis of geometry. What of that? Well, based on geometry axioms, there are a limited number of things you can know. Let's have a definition up here on this little sheet I made. A triangle is isosceles, that is to say, by that we mean at least two of its sides are equal in length. Often, if we want to draw a diagram of a isosceles triangle, we put little hash marks on the two sides that are meant to be equal. So even if our drawing is inexact, as my freehand drawing no doubt is, you get the idea. These two sides are supposed to be known to be equal. Well, a proposition. In any isosceles triangle, two angles are equal. In other words, given two equal sides, we can prove two equal angles, opposite to the two equal sides, as a matter of fact. How do we prove that? From the axioms. In fact, if this proposition were not true, one way of putting it is that if this proposition were not true, one or more of our axioms of geometry wouldn't be true either. And by an axiom, we take, for the sake of our science, geometry, in this case, something being unquestionably true. But only a limited number of things can be known based on the axioms. Look at this, almost trivial question up here. What is the angle ABC? What size is it, in other words? As I said previously, you can know a great deal, very many propositions of geometry by proofs from the axioms. But don't let that go to your head. There are very many propositions of geometry that you cannot know from the axioms, such as this question I have written at the top of the page. Now, that doesn't open us to relativism. There is some truth to the matter. This angle up here is of a definite size, no more, no less. And there is some method, perhaps, of finding out just how big is this angle. For example, a protractor. But, that's not to say that you can know it from the axioms. As I'm emphasizing here at the bottom of the page, you can't know what the truth of the matter is only from the axioms. And that is fundamental to understanding what geometry is. It's a deductive science, an axiomatic science. Till next time.